Welcome to the deep dive where we like to take those complex topics everyone's talking about and make them surprisingly interesting.
Surprisingly, yes.
Today, we're taking a deep dive into deep generative modeling.
Ooh, exciting.
Yeah, it's the tech behind those incredible AI creations everyone's been talking about.
Right. The deep fakes, the AI art.
Yeah, all that stuff. You sent us this dense academic paper on the subject, and I gotta say I was a bit intimidated, to be honest.
Yeah, it can be a little dense, but
But thankfully, expert speaker is here to help us break it down.
don't worry, well, it's not as scary as it looks. I think you'll be surprised by how elegant the math behind this tech actually is. Like, even beautiful in a way.
Beautiful math. Okay, well, I'll trust you on that. But before we get lost in the equations, can you remind me why this stuff even matters? I mean, I get the wow factor of AI making art and stuff, but what's the bigger picture here? Why should we care about this?
Well, think of deep generative models, or DGMs, as neural networks with a bit of a creative spark. They don't just copy data. They actually learn from it and then generate something totally new.
Okay, so it's not just mimicry. It's like what? Artistic inspiration, but for a computer.
Exactly. DGMs, they learn the underlying probability distributions of the data. Essentially, they're figuring out how likely certain features or combinations of features are to appear. And this allows them to create new data that has that same feel as the original, but it's not just a direct copy.
So that's how you get those crazy realistic deep fakes, right? The AI, it like learns what makes a person's face unique and then creates new images or videos that are practically indistinguishable from the real thing.
Precisely.
Wow.
But DGMs can do way more than just deepfakes. Imagine using them to design new drugs.
Oh,
Yeah,
wow.
by generating molecules with specific properties,
Mm.
or creating these hyper-realistic 3D models for video games,
Mm.
or architecture, really, you name it. They could even compose music in the style of Bach, or simulate these super complex scientific phenomena.
Okay, yeah, now that is pretty mind-blowing. But the paper you sent, it made it clear that training these DGMs is no walk in the park, right? What makes it so mathematically challenging?
Hmm. Well, imagine you're trying to bake a cake, right?
Okay.
But all you have is like a few crumbs you
A
found.
few crumbs, okay.
You can try to guess some of the ingredients, but you can't be 100% sure what went into it, right?
Right.
That's kind of similar to what we face with DGMs. We have limited data, and we're trying to figure out the exact recipe or probability distribution that created it. It's what the paper calls the ill-posed problem.
So we're basically working with an incomplete recipe. How do we even get started with that?
Well, it takes a lot of clever math and some serious computational power. But even then, we face another challenge. How do we know if our DGM is baking the right kind of cake?
Hmm. Good point.
We need ways to measure how similar the generated data is to the real data. And this is tricky because we don't have those direct correspondences between data points.
So it's not like we can just line up the cakes side by side and see if they're identical.
Exactly. We need to compare the overall distributions, which is kind of like comparing the flavors and textures of the cakes without actually seeing them directly.
Okay, that makes sense. Now, the paper also mentions this latent space dilemma. What's that all about?
Okay. Uh, Imagine you're trying to draw this super detailed map of a city,
All right.
but you're only allowed to use a tiny piece of paper. You have to figure out how to compress all that information onto it without losing the important details. It's kind of what we do with DGMs.
No, okay.
We assume there's a simpler representation of the data called the latent space, and we need to figure out the right size for this map.
So if our map is too small, we lose detail. But if it's too big, things get messy and confusing.
Precisely. Choosing the optimal dimension for this latent space is really crucial, and often we just don't know the answer beforehand.
It's like we're trying to solve a puzzle with missing pieces and no picture on the box. To help illustrate these challenges, the paper uses two test cases, Moons and MNIST. Can you tell us about those?
Absolutely. The moon's example, it involves teaching a DGM to create data that resembles, well, two half-moon shapes.
Okay.
It seems simple, but it actually highlights the need for the AI to learn those smooth transformations. Even though the data is, split into these two distinct parts, it's like teaching the AI to draw a continuous line that forms two separate moons.
So even though the moons are separate, the AI has to see them as like part of a connected whole.
Exactly. It's
Yep.
all about learning the underlying structure, not just copying what it looks like on the surface. The MNIST example, on the other hand, focuses on generating handwritten digits,
Okay.
a classic challenge in machine learning because the true dimension of the data is actually hidden.
Hidden.
Yeah, it's like trying to figure out how many dimensions a shadow has. Like, it's a projection of something way more complex.
Yeah. And if I remember correctly, the paper uses a 2D latent space for the MNIST example so we can actually see it, right?
Yes, that's right. We can actually visualize how the AI organizes the digits in this 2D space, which can give us some insights into how it's learning.
Okay, so we've got a handle on the challenges now. Now let's talk solutions. The paper dives into three main approaches: normalizing flows, variational autoencoders, and generative adversarial networks. Where should we start?
Hmm. Let's begin with normalizing flows. They're a good entry point because they make this key simplifying assumption. The generator is invertible, meaning we can go from the latent space to the data space and back again without losing any information.
So it's like a perfect round-trip ticket.
Yeah, exactly.
Sounds pretty convenient.
It is. And this invertibility lets us directly calculate the likelihood of our data, which makes training way easier. We don't have to rely on those complex approximations needed for other approaches. The paper discusses two types of normalizing flows: finite and continuous.
What's the difference?
Well, think of finite normalizing flows as like a series of well-defined steps, like following a recipe. Each step is a simple invertible transformation that gradually shapes the latent distribution into the data distribution. Continuous normalizing flows, on the other hand, are more like a smooth, flowing river. They use a trainable, dynamical system to model the transformation, making it much more flexible and adaptable.
And the paper applies both of these to the moon's example, right?
Yes, we can actually see how one type of finite normalizing flow, called real NVP, maps a simple Gaussian distribution to those two half-moon shapes. It's kind of like watching dough transform into those crescent rolls.
Okay, I'm starting to get the picture. But the paper also mentions a limitation with these normalizing flows. Something about the dimensions needing to match, right?
That's right. Normalizing flows work best when the dimension of the latent space matches the dimension of the data. And this could be a problem when we're dealing with complex, high-dimensional data like images. It's like trying to fit a 3D object into a 2D space. You're going to lose some information.
So they're great for specific cases, but not a universal solution.
Exactly. However, normalizing flows can still be really useful as building blocks within more complex DGM architectures. It's like having a specialized tool in your toolbox. You might not use it for every job, but when you need it, it's indispensable.
All right, makes sense. So normalizing flows are great when we have that nice invertibility, but what about when things get messier? What happens when that generator isn't invertible?
That's where variational autoencoders, or VAEs, come in. They take this probabilistic approach, embracing the uncertainty that comes with, working with such complex data.
So instead of trying to find that one exact answer, they give us a range of possibilities.
Precisely. VAEs don't try to find one specific point in the latent space that corresponds to a data point. Instead, they estimate a distribution of possible latent variables. It's like saying, we're not exactly sure where this data point came from, but here's a cloud of likely locations.
Okay, so it's more like a blurry map than a precise GPS coordinate.
Yes, that's a great way to put it. And this approach is super helpful when dealing with those non-invertible generators and high-dimensional data, where that one-to-one mapping just isn't feasible.
So VAEs give us more flexibility when things get complicated, but how do they actually work? The paper mentions something called an encoder.
Right. Think of the encoder as a neural network that maps the data to the latent space. But instead of outputting a single point, it actually outputs a probability distribution, often a Gaussian, representing the possible locations of that data point in our blurry map.
Okay, so it's not giving us a precise answer, but rather a range of likely answers.
Exactly. And this probabilistic mapping is crucial because it allows the VAE to handle the non-invertibility of the generator. We're no longer restricted by that round-trip ticket requirement.
I'm starting to see how VAEs can handle more complex situations, but how do we actually train them? The paper mentions something called the ELBO. That sounds a little intimidating.
Well, it's not as scary as it sounds. The ELBO, or evidence lower bound, is kind of like a clever math trick that helps us train both the encoder and the generator at the same time. Imagine you're trying to measure the brightness of a star,
Okay.
but there's a lot of atmospheric interference. You can't get a perfect measurement, but you can get a lower bound, a guaranteed minimum brightness. That's kind of what the ELBO does. It gives us this lower bound on the data likelihood, which is much easier to work with than the true likelihood itself.
So instead of aiming for a perfect bullseye, we're aiming for a guaranteed hit within a certain range.
Exactly. And minimizing this ELBO actually achieves two things. It improves how well the generator reconstructs the data, and it encourages the latent space to behave nicely, meaning the distribution of those blurry points should resemble the simple distribution we assumed, like our trusty Gaussian.
It's like hitting two birds with one mathematical stone. Now, the paper revisited the MNIST example using these VAEs, and there are some interesting observations, right?
Yeah. The MNIST example, it showed that VAEs can learn these meaningful relationships in the data without being told explicitly what to look for. The VAE clustered digits with similar shapes together in the latent space, even though we didn't give it any labels.
So it's like the VAE is figuring out the underlying structure of the data all on its own.
Exactly. It's a great example of how VAEs can uncover those hidden patterns.
Well,
But there was also a downside. The generated MST images. They were a bit blurry compared to the real ones.
right, like they were missing some of the finer details.
That's likely because we're approximating a potentially complex distribution with, well, just a simple Gaussian. Our blurry map might not be capturing all the nuances of the data, which leads to those less sharp outputs.
So it's a trade-off between flexibility and precision.
You could say that.
Yeah.
VAEs give us flexibility in handling high-dimensional data and non-invertible generators, but we might sacrifice some detail along the way. Now, are you ready to move on to the most talked about approach in deep generative modeling?
You mean GANs. Those are the rock stars of the AI world, right?
They are. Generative adversarial networks, or GANs, take a totally different approach. Instead of focusing on likelihoods or latent variables, they turn the whole training process into this competition between two neural networks.
A competition? Oh, this sounds interesting.
It is. We have the generator, whose job is to create new data that resembles the real data.
Mm-hmm.
And then we have the discriminator, whose job is to tell the real data apart from the generated data.
So it's like a forger trying to create perfect replicas and a detective trying to spot the fakes.
Exactly. And this adversarial training process, it pushes both networks to get better and better. The generator gets better at creating realistic fakes, and the discriminator becomes more skilled at spotting them. It's this constant back and forth that leads to some seriously impressive results. GANs are known for producing highly realistic outputs, often surpassing what other methods can achieve.
But the paper also mentioned that training GANs can be, well, a real headache. What makes it so challenging?
Imagine trying to balance a pencil on its tip.
Okay, yeah.
Incredibly difficult, right? Any little nudge can send it toppling over. Training GANs is kind of like that. We're trying to find that delicate balance between the generator and the discriminator, and it can be super sensitive to changes in the training process.
So if one network gets too good, it throws the whole thing off balance.
Exactly. Finding the right balance is key, and it often involves, well, a lot of careful tuning of hyperparameters in those training procedures. It's a delicate dance, but the rewards can be, well, spectacular.
Okay, so we've got these two networks battling it out, but what exactly is the discriminator looking for? How does it actually tell the real data from the fake data?
Well, there are a couple of ways to do this. The paper talks about two main types of discriminators, those based on binary classification
Mm-hmm.
and those based on transport costs. Let's start with binary classification.
All right, so how does that work in the context of GANs?
In this approach, the discriminator is trained to classify each data point as either real or fake. It's like a simple yes-no question. Did this data point come from the real data set, or did the generator create it?
So the discriminator is essentially learning to spot the telltale signs of a fake.
Exactly. And the generator, well, it's constantly trying to improve its fakes to fool the discriminator.
It's an arms race of deception and detection.
Precisely. Now, the paper applied this binary classification approach to the MNIST example, using a specific GAN architecture called DCG, or Deep Convolutional GAN. And the results were pretty interesting.
What did they find?
Well, the DC-GAN, it produced some remarkably sharp, realistic images of handwritten digits. Some were even indistinguishable from the real MNIST digits. But there was a catch. Some of the generated images were just nonsensical. They didn't seem to represent any recognizable digit at all.
So sometimes the generator gets a little too creative.
Yeah, you could say that. Sometimes it gets stuck in a rut, producing those strange, unrealistic outputs. It's like the forger accidentally inventing a new type of currency that doesn't actually exist.
And the paper mentioned that initializing the generator with the solution from the VAE training actually helped improve the DCGAN's performance, right?
Yes, that's right. It seems that giving the generator a good starting point can help it avoid getting lost in that vast space of possible images. It's like giving the forger a basic template to work with, instead of letting them start from scratch.
Okay, so Binary classification GANs can produce some pretty realistic samples, but they can also get tripped up by those nonsensical outputs. What about the transport cost approach? How is that different?
Okay, so transport cost GANs, specifically Wasserstein GANs or WGNs, use a different metric to measure the distance between the real and generated distributions. Instead of asking that simple yes-no question, they calculate a cost of transporting one distribution to the other. It's like figuring out the effort required to reshape a pile of sand into a sandcastle.
So it's a more nuanced measure of similarity than just saying real or fake.
Exactly. This cost, called the Wasserstein distance, provides a more stable training process and is less prone to those nonsensical outputs. However, calculating this distance in high dimensions can be computationally challenging.
So it's a trade-off between stability and computational cost.
You could say that. Now, the paper applied the WGN approach to the MNEST example as well, and the results were pretty intriguing.
What did they find?
The WGN, it produced images that were just as sharp as those from the DCGAN, and it seemed to suffer less from those nonsensical outputs. But again, initializing the generator with the VAE solution led to even better performance.
So that VAE solution seems to be like a secret weapon for improving GAN performance.
It appears so, like giving those competing networks some common ground to start from.
Okay, so we've covered a lot of ground here. We've explored those challenges of deep generative modeling, and we've delved into three different approaches. Normalizing flows, VAEs, and GANs. Each has its strengths and weaknesses, and choosing the right approach really depends on the specific problem and, the desired trade-offs.
That's a great summary. And remember, this field is constantly evolving. New and improved DGM architectures and training methods are being developed all the time.
It's an exciting area of research, with the potential to revolutionize so many fields. But before we move on to part two, where we'll compare these approaches in even more detail, I want to hear your expert take on something. We've seen how each approach tackles the challenges of DGM training in its own way, but what are the big picture takeaways? What should our listeners really remember from all of this?
I think the most important takeaway is that deep generative modeling, it's powerful but challenging. There's no one-size-fits-all solution. Choosing the right approach depends on the problem and the trade-offs you're willing to make. Understanding the underlying mathematical principles of each approach, well, that's crucial for making those informed decisions and for pushing the boundaries of what's possible with DGMs.
That's great advice. And as always, our show notes will include links to the paper and some visual examples to help solidify these concepts.
And the next time you come across one of those awe-inspiring AI creations, remember there's this fascinating interplay of probability, neural networks, and maybe even a touch of optimal transport, all working behind the scenes.
That's a great way to put it. Now, before we wrap up part one, we want to leave you with something to ponder. We've talked a lot about how these DGMs learn from existing data to create new data.
Right.
But what about the limits of that learning? Can a machine truly understand the essence of what it's creating, or is it just a sophisticated mimic?
That's a deep philosophical question, and one that we'll be exploring further in future episodes. For now, keep that question in mind as you continue on this journey of understanding the incredible power of deep generative modeling.
We'll be back soon with part two, where we'll delve deeper into the nuances of each approach and compare their performance head-to-head.
Until then, happy generating. Welcome back to the deep dive. Before the break, we laid the groundwork, exploring what deep generative models are, those mathematical challenges they face, and the three big approaches researchers are using to tackle them. Normalizing flows, variational autoencoders, or VAEs, and those generative adversarial networks, the GANs.
Right. We saw how each of these approaches has its own quirks, its own advantages. It's like having different tools in a workshop. You wouldn't use a hammer to screw in a light bulb, right?
Right.
Now it's time to put these tools head to head. Let's break down those strengths and weaknesses, figure out which one's best suited for which job.
Okay, sounds good.
Where do we start?
Let's start with those normalizing flows. Their biggest strength is their invertibility, that clear two-way street between the latent space and the data space.
Okay.
But that's also their biggest limitation, because it only works if the data actually lives in a space with the same dimensions as our chosen latent space.
So it's like having this perfectly organized filing cabinet where each file has its own unique drawer. It works great if you have the same number of files and drawers, but what happens if you've got more files than drawers?
Exactly. That's where the limitation kicks in. Normalizing flows, they excel when we have good reason to believe the data's true dimensionality matches our chosen latent space, and that the transformation between them is, well, smooth and reversible. Think of our moon's example, that relatively simple two-dimensional data set. Normalizing flows, perfect fit for this kind of scenario.
They shine in those lower dimensional, well-behaved cases where we've got that one-to-one mapping between data and latent space. But what about when we, venture into the realm of higher dimensions, like with our MNIST handwritten digits? Each image, 784 pixels. It's like trying to fit a giant stack of files into that neat little filing cabinet.
Precisely. And even if we could squeeze them in, the arrangement would be so complex, so tangled, it'd be almost impossible to go back and forth without losing information. That's where VAEs step in, with their more flexible, probabilistic approach.
Right. VAEs are like saying, let's just create a bigger room and spread out the files. We don't need to know exactly where each file goes as long as we have a general idea of where to find it.
That's a great way to put it. VAEs, they embrace uncertainty. They don't require that perfect one-to-one mapping. This makes them way more flexible when it comes to that latent space dimension. Plus, they offer us a glimpse into that latent space, allowing us to see how the data is organized, even without labels.
Like in the EMS example, the VAE managed to cluster similar digits together in that latent space, even though we didn't tell it which digit was which. It's like the VAE is tidying up the room, grouping those similar files together without even reading the labels.
Exactly. It's a powerful way to uncover that hidden structure in the data. But VAEs also have a drawback. Remember those slightly blurry MNIST images? It's like some of the ink smudged when we were spreading out the files.
Right, the VAE captured that general shape of the digits, but some of those finer details were lost. It's a trade-off between flexibility and precision.
You could say that. VAEs give us the flexibility to handle that high-dimensional data in those non-invertible generators, but we might lose some detail in the process. Now, are you ready to enter the arena of those AI gladiators?
You mean Jans?
Yes.
Bring on the drama.
GANs, the rock stars of the generative modeling world. Known for their ability to create those incredibly realistic outputs, they achieve this through that fascinating adversarial training process.
It's like a constant battle between a master forger and a world-class detective, each pushing the other to become better.
Exactly. The generator, our forger, tries to create those fakes that are just indistinguishable from the real data. Well, the discriminator, our detective, tries to, spot the forgeries. This competition, it leads to a constant improvement in both networks.
But as we discussed earlier, training GANs, it's like trying to ride a unicycle on a tightrope. Requires a delicate balance. It can easily go wrong.
Yeah, finding that right balance between the generator and discriminator, that's key. If one network becomes too powerful, it throws the whole system off. It's a high-risk, high-reward scenario. But when it works, the results, they are spectacular.
We talked about two types of GANs. The binary classification approach with the DCGN and the transport cost approach with the WGN. Can you remind us how those differ?
Sure. The DCGN uses a discriminator that simply classifies each data point as real or fake, like a detective giving a thumbs up or a thumbs down.
Okay.
This approach, it can produce those sharp, realistic images, but it's also prone to those nonsensical outputs we talked about.
Right. It's like the forger sometimes creates something completely bizarre, doesn't even resemble the original data.
Exactly.
Hmm.
The WGN, on the other hand, it uses a more nuanced approach. It calculates the Wasserstein distance, which is like measuring the effort required to transform one distribution into another.
So instead of a simple yes or no, the WGN's giving us a more detailed assessment of how similar the distributions are.
Precisely. This leads to a more stable training process and fewer of those nonsensical outplings. However, calculating the Wasserstein distance can be computationally expensive, especially with that high-dimensional data.
It's like the detective needs more time and resources to conduct a thorough investigation.
Exactly. And remember, both types of GANs, they benefited from that VAE solution as a starting point. It's like giving the forger and the detective a shared understanding of the basics before they start their battle.
Okay, so how do we choose the right tool for the job? Seems like each approach has its own pros and cons.
That's right. If we're dealing with that lower dimensional data and a smooth invertible mapping, normalizing flows are a great choice. Offer straightforward training, direct likelihood calculations.
It's like using a precise measuring tool for a simple carpentry project.
Yeah. For those higher dimensions and those non-invertible scenarios, VAEs provide that flexible, probabilistic approach. They might sacrifice some detail, but they offer those valuable insights into the latent space.
It's like using a broader brush to paint a more complex picture.
And for those seeking the pinnacle of realism, GANs are the heavy hitters. but be prepared for the challenges of training those adversarial networks.
It's like conducting a high-stakes experiment, right?
Yeah.
Requires careful planning and execution, but the potential rewards are
Yeah.
enormous. Okay, so let's talk applications. We've hinted at the potential of these DGMs, but now let's dive into some concrete examples. What are some ways DGMs are being used to solve problems, to create amazing things?
The applications, they're vast. They span so many fields. One area where DGMs are making a huge impact is in those creative industries. They're being used to create those photorealistic images, compose original music, generate those realistic 3D models, and even write compelling stories.
It's like giving artists and creators a whole new set of tools to explore their imagination, to push the boundaries of what's possible.
Exactly. Imagine video game designers using AI to create these vast, immersive worlds populated with unique and believable characters. Or musicians collaborating with AI to explore new sonic landscapes.
It's like the line between human creativity and artificial intelligence. It's becoming, well, increasingly blurred.
Yeah, but the applications of DGMs go far beyond art and entertainment. They're also revolutionizing fields like science, medicine, and engineering.
Oh, wow. Can you give us some examples?
Sure. In drug discovery, DGMs are being used to design new molecules with specific properties, potentially leading to the development of life-saving drugs. It's like having an AI chemist who can explore millions of possible molecular structures to find those most promising candidates.
That's incredible. What about other fields?
In material science, researchers are using DGMs to design new materials with enhanced strength, durability, or conductivity. Imagine creating a material that's lighter than steel but stronger than diamond, or material that can conduct electricity with zero resistance.
The possibilities are, well, they're mind-boggling. It sounds like DGMs are unlocking a whole new world of innovation.
They are. And they're even being used to personalize education, creating customized learning experiences tailored to each student's individual needs and learning styles.
It's like having a personal AI tutor who can adapt to your unique learning pace and style.
Exactly. But as we discussed before, with great power comes great responsibility. DGMs have the potential to revolutionize so many aspects of our lives, but we need to be mindful of the potential risks as well.
Right. We can't just blindly embrace this technology without considering the ethical implications. What are some of the potential downsides we need to be aware of?
Well, one concern is the potential for misuse. DGMs can be used to create these incredibly convincing deepfakes, which can then be used to spread misinformation, manipulate public opinion. We need to be aware of this possibility and develop ways to distinguish between the real and the AI-generated content.
It's like the ability to create perfect forgeries makes it even more important to develop methods for authentication.
Exactly. Another concern is that potential impact on jobs. As AI becomes more capable of performing tasks that were previously done by humans, we need to think about the implications for the workforce.
It's a challenge we need to address as a society. How do we prepare for a future where AI plays a more prominent role in the workplace?
Yeah. These are complex questions, no easy answers. But it's essential that we have these open, honest conversations about these issues, involving not just experts, but the wider public.
We need to approach this technology with both excitement and caution, recognizing both its potential benefits and those potential risks.
And we need to work together to ensure that DGMs are used for good, to create a future where AI enhances human capabilities
Yeah.
and improves our lives.
That's a great message to end on. We've covered a lot of ground in this episode, from the mathematical foundations of DGMs to their wide-ranging applications and those ethical implications, but there's still more to explore.
Join us in part 3, where we'll delve even deeper into this exciting world of deep generative modeling.
Welcome back to the deep dive. We've spent the last 2 parts of this episode exploring this fascinating world of deep generative modeling. You know, the math, the challenges, the different approaches. We even dip our toes into those ethical considerations.
Yeah, we've covered a lot. But now it's time to really let those imaginations run wild. Let's talk about the future of DGMs.
Yes, let's. We've already seen how DGMs are being used in those creative fields like art and music and video game design, but where else could this technology take us?
Well, the possibilities, they're truly limitless. Imagine a world where architects can use DGMs to design buildings that are not only aesthetically pleasing, but energy efficient and sustainable as well.
Or, doctors using DGMs to create personalized treatment plans based on a patient's unique genetic makeup and medical history.
Yeah. DGMs could even revolutionize the way we interact with computers. Imagine having a virtual assistant that understands your needs and preferences so well it can anticipate what you want before you even ask.
It's like having a mind-reading AI companion that's both exciting and a little bit creepy at the same time.
Indeed. But it really highlights that incredible potential of DGMs to really transform our lives. Imagine a world where we can use AI to solve some of the world's most pressing problems, from climate change to poverty to disease.
That's a future I can definitely get behind.
And it
But
really,
as we've discussed, we need to, we need to proceed with caution. DGMs are powerful tools, and like any tool, they can be used for good or for ill.
absolutely. We need to be mindful of the potential risks of this technology, from the creation of those convincing deepfakes to the displacement of human workers.
It's crucial that we develop those ethical guidelines and regulations to ensure that DGMs are used responsibly, for the benefit of humanity.
And we need to foster these open and honest conversations about the impact of AI on society, involving not just experts, but everyone.
Because ultimately, the future of AI, it's not something that'll be decided by just a select few, but by all of us.
I think it's important to remember that DGMs, at their core, they're tools for creativity and innovation. They can help us unlock those new possibilities, explore those new ideas, and create things that were once just unimaginable.
It's like giving humanity a new set of paintbrushes and a blank canvas. What we create with those tools, well, it's up to us.
I'm really excited to see what the future holds for deep generative modeling. I believe this technology has the potential to make the world a better, more beautiful, and more interesting place.
And that's a perfect note to end on. Thank you for joining us on this deep dive into the world of DGMs. We hope you've learned something new and maybe even been inspired to explore this fascinating field further.
Until next time, keep exploring, keep learning, and keep creating.